Hi everybody, my name is Shireen and this is my video for Lab 5. The purpose of this lab was to take the tools and methods we've learned this semester and apply them to model a physical system. I decided to model the motion and energy of an elastic collision and an inelastic collision. The results of this lab found that the computational models demonstrated that elastic collisions experience a conservation of kinetic energy and inelastic collisions demonstrate a change in kinetic energy. The physical principles involved in this lab included the momentum principle and the energy principle. Collisions experience a conservation of momentum because there are no external forces acting on the system, so the momentum of the system is conserved. The energy principle states that the change in energy is attributed to the work done by the surroundings and heat. We will go more in depth as to how these principles apply to elastic and inelastic collisions in the next few slides. Perfectly elastic collisions are described as a collision in which there is no net loss in kinetic energy of the system. Both momentum and energy are conserved in this type of collision. A good example of an elastic collision is seen in the image below. This Newton's cradle is transferring the momentum of one ball to another while also conserving the momentum of the system. The energy is similarly conserved from the initial conditions of the ball to the final conditions of the ball. The formula for the conservation of momentum is seen below, where the initial momentum of both objects in the system equals the final momentum of both objects in the system. The formula for the conservation of kinetic energy similarly states that the initial kinetic energy of the objects in the system is equal to the final kinetic energy of the objects of the system. In a perfectly inelastic collision, there is a loss of kinetic energy. Specifically, a perfectly inelastic collision is one in which two objects collide and stick together. The momentum of the system is conserved in an inelastic collision, and the formula is the same as the one that we saw before. However, in an inelastic collision, the kinetic energy of the system is not conserved. There is usually some form of transfer of the kinetic energy from the system into the surroundings. Most often, it occurs in the form of a change in the thermal energy, sound energy, or material deformation. The relevant formula for the change in kinetic energy of a perfectly inelastic collision is 1/2 m1v1 squared plus 1/2 m2v2 squared equals 1/2 m1 plus m2 times vf squared. The image below is a good example of a perfectly inelastic collision. The two objects collide and stick together and begin moving with a different velocity from either of the original velocities. Here is the VPython code for an elastic collision. The system properties were defined, including the position, mass, and momentum of the balls. Next, in the loop, the momentum and positions were updated for the objects. The net force was a derivative of Coulomb's law for particles. Finally, the kinetic energy of the system was plotted on a graph. Here's what the code looks like when it's run. As you can see, the kinetic energy was conserved from right before the collision to right after the collision, demonstrating that this was in fact an elastic collision. This is the code for the inelastic collision in VPython. The inelastic collision was a little harder to model because we had to connect the two objects in the middle with a spring. So the system properties were initialized for the mass, position, and momentum of all three balls and the position of the spring. In the loop, the net force was calculated by adding the derivative form of Coulomb's law to the spring force as seen in the lines of code below. Next, the momentum and position were updated for all three objects, and the position of the spring was updated as well. Finally, the kinetic energy of the system was plotted. This is the result for the inelastic collision VPython code. As you can see, there is no conservation of kinetic energy from before the collision to after. The energy is transferred from the system into the surroundings, which can be seen on the graph below and demonstrates an inelastic collision. Thank you for watching.